Good afternoon. Today we're going to be talking about a project study. So while we usually pick up the air around us as neutral, the air machine actually contains acidic oxide of carbon, nitrogen and sulfur, and the concentration of these oxides has been increasing since the Industrial Revolution. So acidic oxide. So acidic oxides are oxides that react with water to form acids, or in some cases they react with bases to form salts, and usually it's non-metal oxides that behave as acids. Examples of common non-metal oxides that act as acids are carbon dioxide, sulfur dioxide, and nitrogen dioxide, and HO5. So basically what is meant by acidic oxide is that they become acids when they react with water. So in solution, carbon dioxide with water forms carbonic acid, and sulfur dioxide with water forms sulfurous acid, nitrogen dioxide with water forms nitric and nitrous acid, and H2O5 plus water forms phosphoric acid. And you shouldn't get confused with the N2O, CO, and O, which are neutral and not acidic. Similarly, basic oxides are oxides that react with water to form bases or react with acids to form salts. Metal oxides usually behave as bases, and examples of basic oxides are potassium oxide, sodium oxide, and magnesium oxide. So in the same case, you've got they become basic hydroxides when they're in solution, and they are in solution. So this forms potassium hydroxide, this forms sodium hydroxide, and this forms magnesium hydroxide. Amphoteric oxides are oxides that react with both acids and bases. Their behavior depends on the reactions that they are put in. Aluminium oxide is an example of amphoteric oxides. They react with hydrochloric acid to produce aluminium chloride, and they also react with a base, sodium hydroxide, to form sodium aluminate. And this is a diagram showing the trends in the periodic table in regards to acidic, basic, and amphoteric oxides. So the keys here that the ones on the right hand side, apart from the noble gases, are usually acidic oxides, and these are non-metals, and amphoteric oxides are usually only a few, aluminium, zinc, and lead, and the rest form basic oxides usually, and the noble gases don't form any oxide. The chemical equilibrium. Many chemical reactions do not get to completion. Many reactions are reversible and two-directional and can perform can go from left to right, forward, or right to right, or right to left reverse reaction. Reversible reactions reach a position of stability that is called the point of the chemical equilibrium. At this point of equilibrium, there is no longer any change in concentration of the reacting product. The reaction has come to a stop. At the point of equilibrium, there will be both reactants and product present. However, the point of chemical equilibrium is not fixed. It depends on the conditions of the reaction. This is the basis of HSG Revision. So this is a simulation showing that when chemical equilibriums are processing, it's always in the same proportion. So also the HSG principle. Basically, systems at equilibrium have a constant concentration of reactants and products. If conditions change, the system will no longer be at equilibrium, and that's what the HSG principle states. Basically, if a chemical system at equilibrium is subjected to changing conditions, the system will readjust to counteract the change. So the system will always seek a point of equilibrium. So when there is a change, it will readjust to oppose the change and return to a point of equilibrium. So this is a table highlighting the different factors that affect the chemical equilibrium. And so basically an increase in concentration of a substance, a shift is always away from that substance, and this is because the extra concentration needs to be used up. A decrease in concentration goes towards the substance because you have to reform the substance that is removed. An increased pressure usually goes towards the fewer moles to counteract the change, and decreased pressure goes to the higher moles. An increase in temperature, it goes away from the release of heat, and the endothermic reaction is favored. And a decrease in temperature, it goes towards exothermic reactions because the heat needs to be used to make up for the loss. And adding a catalyst doesn't usually shift the equilibrium, but the rates of both the forward and reactions are increased by the same proportion, or the same amount. An example of an equilibrium is a solubility of carbon dioxide in water, which is a reversible reaction. It's an exothermic reaction. So the effect of concentration, according to LCP, if the concentration of carbon dioxide is increased, the system will dissolve more carbon dioxide to counteract the change, hence the equilibrium will shift to the right. And if the concentration of CO2 is decreased, the system will release more CO2 to oppose this loss, hence the equilibrium will shift to the left. And pressure, if the pressure is increased, the equilibrium will favor the side that reduces the pressure, and that is a forward reaction. It reduces pressure when dissolving carbon dioxide solutions to make up less volume than gases. And if the pressure is decreased, the equilibrium will favor the side that increases the pressure, and that is the reverse reaction. It increases the pressure as the carbonic acid changes back to gaseous CO2 and water. The effects of temperature, because it's exothermic, if the temperature is increased, the equilibrium will favor the endothermic reverse reaction, as in the endothermic it will oppose the change by cooling the temperature. And if the temperature is decreased, it will favor the forward reaction, which is exothermic, and it will heat the system to counteract the change. Finally, the effects of acids on this system. Basically, according to LCP, if an acid is added, the concentration of hydrogen ion will increase, and hence the equilibrium will shift to the left, so it will move away from the hydrogen ion. And if a base is added, the hydroxide ions will react with hydrogen ions, creating water, shifting the equilibrium to the right, as more hydrogen ions are produced to counteract the change. If enough basic substance is added, the reaction could eventually go to completion and no longer have an equilibrium point.
Well, so the board of study chemistry syllabus requires us to learn two specific compounds, including sulfur dioxide and oxides of nitrogen. And the natural sources of SO2 include volcanoes and geothermal hot springs. And the industrial man-made process includes combustion of fossil fuels containing the element sulfur. And oxides of nitrogen, NOx's, the natural source include lightning and bacteria. And combustion, the industrial source is combustion through the combustion chain under high temperature. Alright, so the chemical reactions which release sulfur dioxide include decomposing of organic matters producing hydrogen sulfide, which reacts with the oxygen in the environment to produce sulfur dioxide. So because the syllabus said chemical reactions, it's best to know more than two, minimum of two. So this is the one that I explained just now. And the following here is just a normal combustion. Sulfur solid reacting with oxygen and gas to produce sulfur dioxide. And the release of NOx's include nitric acid, production of nitric acid with the reaction of nitrogen gas and oxygen gas to produce 2 moles of nitric oxide. And the nitric oxide is used to react with oxygen gas in the air to produce nitrogen dioxide, both of which are NOx's, oxide of nitrogen. So the evidence indicating atmospheric concentration of these compounds include chemical instruments which was invented after the 1970s. So hence any data that was collected from this day before 1970, those data are unreliable. And to compensate for this unreliable data, ice core samples extracted from Antarctica were used to show that N2O has been increasing in the atmospheric concentration. Yep, this is just a sample ice core. As you can see, the gray shades represent the concentrations. And and also a direct physical observation that you can see from the environment is photochemical smog, which NO2 is a contributor to this formation, and also increasing acid rain from the rain also shows that there has been an atmospheric concentration increase in NOx and SO2. Acid rain is rainwater that has pH of lower than 5, and the formation of acid rain include sulfur dioxide from human production or natural source, reacting as oxygen to produce sulfur trioxide, which is then used up as one of the product reactants with water to produce sulfuric acid, which is acidic in itself. And this is one of the damages that can be caused due to the rise of NOx's and SO2. It can cause destruction to forests and the increase in acidity of lakes and ocean, which can kill organic aquatic life. And also these strong acid rains can cause erosion to rivers.
Okay, that's an example of the HC question from 2015 about the equilibrium. So this equation describes an equilibrium reaction occurring in a closed system under which set of conditions with the highest yield of Z will be obtained. So there's two factors to consider. There's temperature and pressure. In terms of temperature, because this is endothermic, increasing the temperature will favour the forward reaction, so it will favour the production of higher yields of Z, because it increases temperature and that temperature has to be absorbed, so that comes right to change. And in terms of pressure, because there is 4 moles of Z on the right and there's only 2 moles of X and Y on the left, an increase in pressure would actually shift away from Z, so you want lower pressures and higher temperatures, which is why the answer should be C. Temperature of, okay, and this one is also another equilibrium question, and it asks which of the following would increase the yield of nitrogen dioxide. Adding a catalyst, as we said, doesn't increase the yield. Decreasing the volume of the reaction vessel, decreasing the volume usually increases the pressure, and that will shift to the left. It does not increase this, so it's not B as well. Raising the temperature of the reaction vessel, that would be an answer, because raising the temperature would shift to the endothermic forward reaction to absorb the added temperature, and that's why the answer is C.